On the 21st of July, 2023, somewhere inside a windowless control room in Pasadena, California, a mission engineer typed a routine sequence of commands and sent them across the solar system without a second thought. It was the kind of task performed hundreds of times before. A small correction, a housekeeping instruction, nothing that should have mattered. But this time, buried inside that sequence was a single line that would tilt the antenna of the most distant human-made object in existence by just 2 degrees. 2 degrees. That is all it took. 12.4 billion miles away, in the black void beyond the edge of the solar wind, Voyager 2 obeyed the command exactly as it was told, and in doing so, pointed its dish away from Earth and stopped talking to us. Nobody in that control room understood in that first instant the scale of what had just happened. There was no dramatic alarm, no flashing red warning across a giant screen the way it happens in films. There was only silence. A silence that, on paper, looked like nothing more than a missing data packet. But that missing packet meant something enormous. It meant that a spacecraft launched during the presidency of Jimmy Carter, a machine older than the internet, older than most of the engineers now responsible for it, had gone deaf and mute at the same time, adrift in interstellar space with no way to hear Earth and no way to be heard. To understand why this moment mattered so much, you have to go back to where Voyager 2 came from. Because this was not simply an old satellite losing signal. This was the far end of one of the most audacious journeys ever attempted by our species. Voyager 2 left Earth on August 20th, 1977, 16 days before its twin, Voyager 1, even though it carries the number 2. It launched to take advantage of an alignment of the outer planets that occurs roughly once every 175 years, a celestial coincidence so rare that NASA's engineers built an entire mission around exploiting it. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a spacecraft could slingshot from one to the next, borrowing gravity and momentum at each stop, without needing enough fuel to make the trip on its own. It became known as the Grand Tour, and Voyager 2 remains, to this day, the only spacecraft in human history to have flown past all 4 giant planets. It photographed the eye-like storms of Jupiter and rewrote what scientists understood about volcanic activity on the moon Io. It swept past Saturn's rings, revealing structures within structures, waves and braids of ice and rock that no one had predicted. In January of 1986, it reached Uranus, a planet so far away that sunlight takes over 2.5 hours to arrive there, and discovered 10 new moons along with a magnetic field tilted at a strange and unexplained angle. Then, in August of 1989, it became the only spacecraft ever to visit Neptune, capturing the deep blue storms of the Great Dark Spot and the icy geysers erupting from Triton, Neptune's largest moon. After Neptune, its planetary mission complete, Voyager 2 kept going. It did not stop, did not slow, did not turn back. It simply continued outward, into the emptiness that lies beyond the last planet, carrying with it the golden record, a phonograph disc engraved with the sounds of Earth, greetings in 55 languages, birdsong, laughter, a mother's kiss, a message built for anyone or anything that might one day find it. For nearly 3 more decades, Voyager 2 kept moving through the outer edges of our solar system, through the region dominated by the sun's magnetic influence, a bubble of charged particles called the heliosphere. And then, on November 5th, 2018, it crossed a boundary that only one other human object had ever crossed before it. It passed through the Heliopause, the true edge of the sun's domain, and entered interstellar space, the vast region between stars where the material is no longer shaped by our sun, but by the ancient remnants of exploded stars and the slow drift of the galaxy itself. Voyager 1 had made that same crossing 6 years earlier, in 2012, but Voyager 2 carried something its sibling did not. Its plasma science instrument was still functioning, still alive, still capable of directly measuring the density and temperature of the material surrounding it. For the first time, humanity had a working sensor sitting in the space between stars, sending back real numbers instead of assumptions. This is the machine that went silent on that July day in 2023. Not a dead relic. Not a piece of space junk drifting without purpose. A still functioning scientific outpost, older than most of the people monitoring it, positioned in a place no other operating instrument had ever occupied. Suddenly unreachable. When the loss of signal was confirmed, the mission team at NASA's Jet Propulsion Laboratory understood immediately what had gone wrong, even if understanding the cause did nothing to fix the problem. The 2-degree tilt was enough. At a distance of 12.4 billion miles, Voyager 2's radio signal, even at full strength, spreads out so thin by the time it crosses that gulf that any misalignment of the antenna sends it missing Earth entirely. The spacecraft's high-gain antenna, a dish nearly 4 meters across, had to be pointed with extraordinary precision measured in fractions of a degree, because even the smallest deviation meant the signal would sail past our planet into the emptiness beyond, never to be picked up by anything. There is something almost unbearably human about the way that single command was written and sent. It was not the product of malice, not the result of some catastrophic system failure, not a meteor strike or a solar flare or any of the dramatic hazards popular imagination assigns to deep space missions. It was a typo, in the broadest sense, a small human error embedded in a sequence of instructions meant to do something else entirely. A correction to the spacecraft's antenna elevation that overcorrected just enough to send the dish drifting off target. The command executed exactly as written, exactly as any well-built machine is supposed to execute a command, without judgment, without the ability to question whether the instruction made sense. Voyager 2 did not malfunction. It obeyed perfectly. That is what made the moment so unsettling to the people responsible for it. The spacecraft had done nothing wrong at all. The spacecraft itself had no way of knowing anything was wrong. It was simply doing what it was told, its onboard systems continuing to operate exactly as programmed, running scientific instruments, maintaining power balance, following its last known instructions, all while the antenna sat pointed at a patch of empty space instead of the pale blue dot it had left behind 46 years earlier. From Earth's side, the Deep Space Network, the system of giant radio dishes in California, Spain, and Australia that maintains contact with every deep space mission NASA operates, listened and heard nothing. Not static, not a weak trickle of data, nothing at all. A spacecraft that had survived 4 planetary flybys, a spacecraft that had operated for nearly half a century, appeared to have vanished into the dark. The engineers at JPL had faced antenna problems with Voyager 2 before, but never quite like this. In 2020, the spacecraft went through an 8-month stretch without contact while the one Earth-based antenna capable of communicating with it, a 70-meter dish in Canberra, Australia known as Deep Space Station 43, underwent critical upgrades. That earlier gap had been planned, expected, survivable, because Voyager 2 was simply told in advance what to do and left to continue its work uninterrupted, checked on periodically through smaller antennas that could listen but not transmit complex commands. This new situation in July 2023 was different. This was not planned. This was not scheduled. This was an unintended consequence of a routine command, and there was no way to warn the spacecraft, no way to tell it what had happened, because the only way to talk to Voyager 2 was through the very antenna that was now pointed in the wrong direction. For days, the situation sat in a kind of technological limbo. The spacecraft was not lost in the sense of being destroyed or malfunctioning. It was simply turned the wrong way, drifting through interstellar space, continuing its orbit around the galactic center along with everything else in the solar system, oblivious to the fact that the only civilization capable of hearing it had gone quiet on the other end. Voyager 2's own programming included a kind of built-in insurance policy, a failsafe called the Interstellar Contingency Plan, designed to automatically reset the spacecraft's orientation and repoint its antenna toward Earth if it went a certain length of time without hearing from home. But that failsafe was not due to trigger until October, months away. Waiting for it meant months of silence, months of uncertainty, months in which anything could happen to a machine running on plutonium power that had already outlived every original estimate of its lifespan by decades. NASA's engineers were not willing to simply wait. Instead, they turned to a method rarely used, reserved for situations exactly like this one, something that came to be informally known inside the Deep Space Network community as the Interstellar Shout. Rather than relying on Voyager 2's regular low-power communication protocol, the team prepared to blast an extraordinarily powerful and precisely aimed signal from Earth toward the spacecraft's last known position, at a strength far beyond what is typically used, essentially attempting to make sure that, even with the antenna misaligned by 2 degrees, some sliver of the transmission might still be picked up by Voyager 2's more modest, lower-gain receiving systems. On August 1st, 2023, that signal was sent from the 70-meter dish in Canberra, Australia, the same facility responsible for the 2020 upgrade gap, the only antenna on the planet with the raw transmitting power needed to attempt something this audacious. Because Voyager 2 sits so far away, the signal itself would take 18.5 hours simply to arrive, and if the spacecraft managed to detect it and respond, that response would need another 18.5 hours to travel back to Earth. In total, the team faced a wait of 37 hours before they would know whether the Interstellar Shout had worked, whether the oldest continuously operating deep space mission in human history could be pulled back from the edge of permanent silence, or whether it was gone for good, still transmitting scientific data into a void that Earth would never hear. The Deep Space Network itself is worth pausing on, because it is easy to take for granted the infrastructure that makes any of this possible at all. It consists of 3 complexes, spaced roughly 120 degrees apart around the globe, one in Goldstone, California, one near Madrid, Spain, and one outside Canberra, Australia, positioned deliberately so that as the Earth rotates, at least one facility always has a clear line of sight to any given spacecraft, no matter where it sits in the sky. The 70-meter dish in Canberra, the one that carried out the Interstellar Shout, is among the largest steerable parabolic antennas on the planet, built originally in the 1970s and continuously upgraded ever since, precisely because missions like Voyager were never expected to still be operating this far into the 21st century. Aiming that dish at a target 12 billion miles away is not simply a matter of pointing it at a fixed spot in the sky. The antenna must track the spacecraft's calculated position with extraordinary precision, accounting for the Earth's rotation, its orbit, and the spacecraft's own continued drift outward, all while compensating for a signal delay measured not in seconds, but in the better part of a day. Those 37 hours stretched across the control room like something out of a slow-motion countdown, except there was no clock ticking down to a known ending. There was only the physics of distance, immovable, indifferent to urgency. Engineers who had spent careers working on this single mission sat with the knowledge that nothing more could be done in that window. The command was already crossing the solar system. The outcome had, in a strange sense, already been decided the moment the signal left the dish. All that remained was waiting to find out what that decision had been. On August 6th, before the full response window had even closed, something changed. Voyager 2's carrier signal, a faint but detectable heartbeat that the spacecraft continuously emits even when it is not transmitting structured data, was picked up faintly by Earth-based listening stations. It was not full communication, it was not confirmation that the interstellar shout had succeeded, but it was proof of something critical. Voyager 2 was still alive. Its transmitter still worked. Its power system still functioned. Whatever had happened to the antenna, the spacecraft itself had not failed. Then, on August 4th, 2023, full two-way communication was restored. The interstellar shout had worked. Voyager 2, sitting in the dark between the stars, had picked up Earth's deliberately oversized, deliberately desperate signal, and its onboard systems had responded by reorienting the antenna back toward the source. Telemetry data began flowing again. Scientific instruments confirmed they were functioning normally. The spacecraft reported no damage, no degradation beyond what was already expected from decades in the harsh radiation environment beyond the solar system. A machine, built with 1970s technology, using computers with a fraction of the processing power of a modern calculator, had been talked back from the edge of permanent isolation using little more than raw transmitter power and 18.5 hours of patience twice over. What makes this moment matter is not simply that a spacecraft was saved, it is what that spacecraft has continued to reveal since then, because Voyager 2's survival was never really about nostalgia for an old machine. It was about preserving the only working sensor humanity has ever placed in the space between stars that can still directly sample its environment. Since the antenna crisis was resolved, Voyager 2's plasma science instrument has continued sending back readings from a region of space that remains almost entirely unmapped by direct measurement. Scientists have used this data to compare the interstellar medium encountered by Voyager 2 with what Voyager 1 measured after its own 2012 crossing, and the differences have been genuinely surprising. The density of plasma in the region Voyager 2 passed through has shown fluctuations that do not perfectly match earlier models of the Heliopause boundary, suggesting that the edge of the sun's influence is not a smooth, uniform shell, but something closer to a turbulent, uneven frontier, shaped by pressure from the surrounding interstellar material in ways that vary significantly depending on direction and time. Magnetic field data recorded by Voyager 2 has offered further evidence that the transition into interstellar space involves complex layers of magnetic reconnection, small-scale storms occurring at the literal edge of our solar system, invisible to any instrument except the ones now sitting directly inside that boundary. None of this would have continued if the antenna crisis of July 2023 had ended differently. If the interstellar shout had failed, if Voyager 2's failsafe system had not been backed up by that desperate, oversized transmission from Canberra, the spacecraft's own internal contingency programming would still have eventually reset its orientation in October of that year, months later. But months of silence, for a spacecraft already operating on the thinnest possible power margins, carried real risk. Every additional week without confirmed contact was a week in which an undetected fault could have gone unnoticed and unaddressed. A week in which humanity's only active listening post in interstellar space could have drifted permanently out of reach, not through any single catastrophic failure, but simply through the slow accumulation of uncertainty in a place too far away to inspect, too far away to repair, too far away for anything but light and radio waves to travel back and forth across the gap. Even now, having survived that scare, Voyager 2 exists on borrowed time in a very literal sense. It is powered by a radioisotope thermoelectric generator, a device that converts the heat produced by the natural decay of plutonium-238 into electricity. That decay never stops, and it never speeds up on command, which means the power output of Voyager 2 has been quietly, predictably declining since the day it launched, losing roughly 4 watts of available power every single year. NASA's engineers have spent the last several years managing that decline through a series of difficult decisions. systematically switching off individual scientific instruments one after another, not because those instruments have failed, but because there is no longer enough power to run everything at once. The infrared and ultraviolet spectrometers were shut down years ago. Other instruments have followed, each shutdown extending the operational life of the instruments that remain, buying additional years for the mission at the cost of narrowing what it can still observe. The plasma science instrument, the very sensor responsible for measuring the interstellar medium that makes Voyager 2 so scientifically valuable, remains one of the last still running, prioritized precisely because it is irreplaceable, because there is no other operating spacecraft positioned anywhere close to where Voyager 2 now sits. The golden record itself deserves a moment of its own within this story, because it is easy to mention it in passing without appreciating what it actually represents. Assembled under the direction of astronomer Carl Sagan and a small team of collaborators in 1977, the record is a 12-inch gold-plated copper disc designed to survive essentially unchanged for 1 billion years or more in the vacuum of space. Etched into its surface are instructions, in symbolic diagrams rather than any spoken language, explaining how to build a device capable of playing it, along with a stylus and cartridge included with the spacecraft for exactly that purpose. The sounds encoded on it range from the mundane to the profound. The rumble of thunder, the crash of surf against a shore, a mother's first words to her newborn child, whale song, laughter, greetings recorded in 55 human languages. And 90 minutes of music spanning cultures and centuries, from Bach to Chuck Berry to traditional recordings from Africa, Asia, and the Pacific. It was never built with the expectation that anyone would find it soon, or perhaps ever. It was built as a kind of message in a bottle thrown into the largest ocean imaginable, a deliberate act of optimism from a species that, even while arguing and warring among itself, chose to introduce its better instincts to whatever might be listening out there in the dark. Current projections suggest that Voyager 2 will be able to keep at least one scientific instrument operating into the early 2030s, at which point the declining power supply will finally fall below the threshold needed to run anything at all. When that happens, the spacecraft will not explode, will not break apart, will not suffer any dramatic final moment. It will simply go quiet, its transmitter falling silent for the last time, its scientific instruments powering down one by one until nothing remains active. But Voyager 2 itself will not stop moving. It will continue drifting outward, carrying the golden record with it, traveling through interstellar space for hundreds of thousands, perhaps millions of years, long after every trace of the civilization that built it has changed beyond recognition, long after the antenna dishes in Canberra and California have crumbled into dust, long after anyone still remembers the specific sequence of events that unfolded over a handful of days in the summer of 2023, when a 2-degree tilt nearly ended one of humanity's longest conversations with the universe, and a desperate shout across 12 billion miles of empty space brought it back just in time. The story of that silence and of the interstellar shout that broke it is easy to read as a footnote. A brief technical scare quickly resolved and largely forgotten outside the small community of engineers who lived through those 37 hours of uncertainty. But it is worth sitting with what actually happened in that moment, because it captures something rare about the entire Voyager program. Here is a machine, designed and built before most of us were born, using technology that would be considered primitive by any modern standard, still capable of receiving a command from home, still capable of understanding it, still capable of correcting its own path, across a distance so vast that light itself needs more than 18 hours to cross it. And here on Earth, still willing, nearly 50 years after launch, to spend the resources, the attention, and the raw transmitting power necessary to reach out into that darkness and pull it back. Voyager 2 did not know it had gone silent. It did not know it had been found again. It simply continued doing what it was built to do, measuring, recording, transmitting, following instructions sent from a planet it left behind in 1977, a planet that, in the decades since, has changed almost beyond recognition, while the spacecraft itself has remained in its own quiet, mechanical way, exactly what it always was. Humanity's furthest working messenger, still listening, still speaking, still moving outward into the space between the stars, carrying a message that may never be answered, to an audience that may never exist, for as long as its dwindling power allows it to keep going.